Welcome to today's Explainer. We're doing a deep dive into something that is quite literally foundational to your project budget. We're talking about structural layout traps. You know, those invisible, seemingly minor decisions made during early design that end up burying millions of dollars in steel inside buildings way before a single shovel even hits the dirt? It's an absolute reality in this industry, and honestly, it's staggering. Think about this number, 37%. A massive 37% of a steel frame's total installed cost is permanently locked in during the early schematic design phase. That's the power of these invisible layout traps. Okay, wait, let's pause right there, because that sounds completely counterintuitive to most project managers. You're saying that before we even have a detailed, finalized blueprint, we've already committed over a third of the structural budget? Precisely. The general layout, your grid spacing, your choice of frame type, those early broad strokes decisions dictate absolutely everything else down the line. And if you make the wrong assumptions right at the start, no amount of clever value engineering later on is going to save your budget.
That really brings up a fascinating iceberg analogy when we break down the total installed cost. The tip of the iceberg isn't what sinks the ship, right? Exactly. This cost breakdown is the key to understanding everything we're exploring today. If you look at just the material weight, it's only 27% of the total cost. It's just the tip. But then you have fabrication at 33% and erection at 27%. When you combine those, the hidden, below-the-surface realities of shop labor, complex cutting, welding, and field assembly swallow up 60% of your total installed cost.
So when an architect or a developer is evaluating early estimates, they're usually just looking at the sheer weight of the steel, right? They're totally missing the bottom of the iceberg.
Yes, and that is a massive trap. They rely on these primitive, weight-based estimates. But steel isn't bought by the pound like flour at a grocery store. The true cost is in the agonizing labor required to actually put all those pieces together.
Which brings us perfectly to our first major pitfall, the weight myth. Right. This is the incredibly common but totally false assumption that less steel automatically equals less cost. The tension between depth versus weight is where projects really start hemorrhaging money.
It's a classic battle, the least weight frame versus the least cost frame. It sounds like they should be the exact same thing, but they really aren't.
Not at all. Let me use a physical analogy here, because I think it makes the physics a lot more relatable. Imagine trying to carry a really heavy box, but you're forced to hold it with your arms bent up tight close to your chest. Your muscles, your joints, they're under massive, constant stress, right?
Oh, absolutely. You'd burn out in minutes.
Well, that's exactly what happens when you force a structural engineer to use a really shallow, lightweight beam just to squeeze out a few extra inches of ceiling height. To make that shallow beam actually hold up the building, the steel fabricator is forced to weld heavy continuity plates and doubler plates deep into the column joints just to manage the extreme stress.
So the joints are forced to do all the agonizing heavy lifting.
Precisely. And that is where your hidden labor costs start piling up. Now imagine carrying that exact same heavy box, but this time you lock your arms straight down. Your skeleton, your bones do the work, and your joints can finally relax. That is the least cost frame. By using a slightly heavier, deeper beam, the sheer geometry of the steel itself handles the load. You completely bypass the need for those expensive, labor-intensive welded plates.
The data on this is literally mind-blowing. By intentionally adding 7% more total steel tonnage to the project, you actually drop your final bill by 14%.
Yup, because you just strategically eliminated the most expensive chunk of that iceberg we talked about, the highly complex fabrication labor.
Okay, moving on. We run into the second major hurdle, irregular grids.
Yes. This is where big architectural ambition violently clashes with structural reality. And it inevitably leads to a phenomenon called worst-case standardizing.
When you analyze a typical complex floor plan, it honestly looks like a chaotic jigsaw puzzle. And it's a very expensive puzzle to solve. When a design features severe column misalignment, or maybe massive sweeping open lobbies, you end up creating a few highly stressed, really awkward structural bays. Now, because it's an absolute logistical nightmare to order 50 different custom deck sizes and beam depths for just one floor, the engineer is backed into a corner. They have to standardize everything based on the absolute worst-case bay.
Meaning, they literally size the materials for the entire floor based on that one terrible, highly stressed section?
Exactly. The tail wags the dog. Just because of a few unfavorable bays caused by column misalignment, typical complex buildings end up wasting roughly 15 to 30% of their total structural capacity. You are permanently burying perfectly good, highly expensive steel capacity into areas of the floor plan that simply don't need it, just to make the building constructible.
So the core takeaway here is the stark contrast between those complex, chaotic layouts and highly optimized regular grids.
The numbers just don't lie. By pushing back against the urge for unnecessary geometric complexity and really embracing regular grids, structural engineers are freed up to truly optimize the decking and the spans. They aren't held hostage by worst-case standardizing anymore. And the result? You can slash the structural frame weight by up to 50% and cut your costs by a quarter. It really hammers home that good early-stage design isn't just about making rendering look pretty. It requires a deep, uncompromising understanding of the economic trade-offs hiding inside your architectural layout.
Let's shift gears to our third trap, which is frame misapplication. And this usually manifests as an epic structural showdown: moment frames versus braced frames.
It's fascinating to see how the economics of these two systems completely flip depending on building height. If we look at shorter structures, say 4- and 8-story buildings, braced frames are the clear winner, right?
Oh, for sure. Up to about 8 stories, braced frames consume only about 87% of the steel weight compared to a moment frame. But here's the trap: moment frame overuse, or underuse. As buildings get taller, say in the 12 to 16-story range, the dynamic completely inverts.
Yes, suddenly the braced frames become 35 to 45% heavier than the moment frames. What exactly is going on there?
Displacement regulations. As a braced frame building gets taller, wind and seismic forces make it want to sway. To meet extremely strict building codes for roof drift, the engineers are forced to massively beef up the thickness of those diagonal braces. The weight, and subsequently the cost, skyrocket exponentially. So by the time you hit 12 stories, the moment frame suddenly steps in as the much more optimized, economical choice. If you don't map this specific transition out during schematic design, you will completely blow your budget out of the water.
That brings us to trap number 4, the bespoke illusion. This is the incredibly dangerous habit of treating every single building like it's a permanent, custom-made sculpture rather than an engineered system. So how do project teams shatter that illusion? It seems to come down to a shift toward modular optimization strategies. Absolutely. If you want to reclaim that 20% margin we've been talking about, teams have got to adopt modular thinking. Think about standardizing repeatable module sizes. When you do that, you open the door to factory automation. When robotic systems can handle the heavy cutting and welding in a highly controlled shop environment, you eliminate a massive amount of expensive, unpredictable field labor variables. One thing that really stands out is utilizing bolted connections for disassembly. That is a massive paradigm shift in how we think about a building's entire life cycle. It's the circular economy in action, and it's brilliant. Instead of permanently welding a frame together so that it eventually just has to be violently demolished and scrapped in 50 years, you bolt it. It can be unbolted, cleanly disassembled, relocated, or repurposed down the line. When you combine that with sourcing recycled steel locally, you dramatically lower your life cycle embodied carbon impact, all while actively amortizing your initial capital investment.
All right, so we've diagnosed the traps. We know what's draining the budgets. Now, what is the ultimate solution? To bridge the agonizing gap between architects, developers, and engineers, we have to turn to analytical estimation.
To actually rescue that 20% margin, there are 3 critical steps teams need to take. Number 1, maintain regular grids. And number 3, standardize for modularity. But let's really hone in on step 2, because that seems like the linchpin. Run automated early-stage analytical cost estimates. I cannot stress this enough. This is the game changer. We absolutely have to abandon those primitive weight-based estimates we talked about at the beginning. Today, we have sophisticated cloud-based analytical tools that can ingest an early architectural model, rapidly run automated connection detailing in the background, and spit out real, labor-inclusive fabrication costs in near real time. So instead of a project manager just guessing based on raw steel tonnage, the software is actually calculating how much welding, cutting, and labor is required well before the design is even finalized? Exactly. Project teams can finally see the invisible fabrication costs before they become permanent, irreversible budget line items. It empowers the architect and the structural engineer to rapidly test different grid layouts and frame types and instantly see the true financial impact of those choices.
Which leaves us with a provocative question to challenge your team with at your next project kickoff. Are your early design choices actually building a structure, or are they just burying your budget? It is arguably the most important question a developer or project manager can ask during schematic design. You have to force your teams to look past the sheer weight of the steel, demand regular grids, and actively use early-stage analytical estimating tools. If you do that, you'll leave the schematic design phase with maximum efficiency, minimal waste, and you just might get that 20% margin back. Thanks for joining us on this explainer. We hope it changes how you look at your next big project. We'll see you next time.